All right, so I want to work our way towards a definition with you. So let's suppose that f has an isolated singularity at z naught. If you have an isolated singularity at z naught, then you're analytic on a deleted neighborhood around z naught. And so that means that you're guaranteed that f has a Lorentz series representation. Let's write it down. F of z equals the sum. I'm going to write it combined as one series, so I'm going to combine the positive negative parts and say n equals minus infinity to infinity coefficient cn z minus z naught to the n. Please keep in mind this is saying n is going from minus infinity to infinity. So I've got the positive powers, n equals 0 gives me a constant, and then I've got also the negative powers of z as well. All right, and so this is valid for, this representation is valid for, well, z minus z naught. It's got to be bigger than 0 because we're deleting z naught, and then less than some radius r. Let's just say for some real number r bigger than 0. Okay, so far so good. So when you have an isolated singularity, you know you have a Lorentz series representation on some little bubble, some deleted neighborhood around this point z naught. And so that brings us to a definition. So we're going to call the coefficient c1. By the way, please realize c1 is the coefficient of z minus z naught to the negative 1. Oops, yeah, and that shouldn't be c1. c minus 1. The coefficient of z minus z naught to the minus 1, which is 1 over z minus z naught. Call this the residue of f at z naught. So just to be clear on notation, c to the minus 1, we're going to write often as res z equals z naught of f of z. So this is saying the residue of f of z at z equals z naught. And it's just the coefficient, it's the coefficient of the minus 1 power of z. And so I thought we should compute a residue real quick. So I've gone ahead and wrote down the series for you. So I want us to find the residue of this function f of z is z squared sine 1 over z. We've played with this function already. We developed this ourselves in the last video series. So we started with sine of z, and then we plugged in 1 over z, and we got this, and then we multiplied by z squared, and we get here. And so you ought to be able to look at the screen and pick out the residue right now. Pause the video if you want to. And so hopefully you can see that the residue at z equals 0 of f of z is negative 1 over 3 factorial, or just negative 1 over 6. And I guess I just said find the residue. Here, yeah, I said the residue at z equals 0, but even if I didn't specify at z equals 0, I've centered my Lorentz series around 0. So that would tell you that I'm interested in the residue at 0. Those have to line up. They have to be the same. So let's go just a little farther in this video. And I want to remind you of an example that we did. I think it was the second lecture series that I gave. It was the lecture series before we all left for the pandemic. And we actually computed the integral of 1 over z minus z naught to the n around a circle. This is just a circle centered at z naught with positive orientation. I'm always going to assume that my circles here have positive orientation unless otherwise specified. And so we worked this out, and we ended up with two cases. We ended up getting 2 pi I exactly when n equals 1, and then we had 0 anytime that n wasn't equal to 1. So if n was positive 5, if you had z minus z naught to the 5th and you integrate, you're going to get 0. If n was negative 3, right, negative n's the way that I've written it, negative n's actually puts you upstairs. Those all go to 0. The only power of n that doesn't integrate to 0 was a 1 downstairs. Remember doing that? And we actually worked that out. We parameterized the circle, and we worked it out like just very hands-on. And later in the course, we pointed out to you, look, this actually works for any closed curve around z naught. If you have z naught and you have any closed curve around z naught, it doesn't matter whether it's a circle or not, as long as it's a closed curve. We're going to assume positive orientation, then you're going to get 0. You don't need a circle. I just write it because it's easier notation to write down. So let's keep that in mind. So let's go ahead now, and I'm going to go ahead and assume that f has an isolated singularity at z naught, and that means that my function f has a Lorentz series representation. I can write f like this, okay, and I can do this on this punctured disk centered at z naught, radius r, and we're going to delete z equals z naught. That's what the bigger than 0 means, delete z equals z naught. Okay, so let's assume that, and maybe we can draw a picture. So here's my picture that I'm working over, and this Lorentz series that I have is valid anywhere inside this disk. So now I'm going to pick a green, and I'm going to draw a curve. For me, the letter C looks green, so we're going to draw this. We're going to draw this curve C in green, and let's just do positive orientation, whatever. Okay, so I'm going to pick some closed curve with positive orientation C inside this bubble. And now I'm going to ask you to integrate the function f of z over C. And if you recall, we said that you can integrate Lorentz series term by term. So first off, C lives inside this disk, so I can use my Lorentz series representation and say, okay, the integral over C of f of z dz is the same as the integral over C of the Lorentz series, n equals minus infinity to infinity, C to the n, C sub n, z minus z naught to the n dz. We said we can integrate term by term, so I can write this as the sum n equals minus infinity to infinity, C sub n integral over C, z minus z naught to the n dz. Now, maybe when I wrote down my example back up here, I should have put the n upstairs and then said 2 pi I when n is -1 and 0 otherwise, whatever. This is how we did it originally. We're going to have to translate it slightly, but you guys can handle that. So I go down here and I say, well, gosh, I recognize this. This is a closed curve. It's around z naught, and I know that this integral is going to be 0 except when n equals -1. Oh my goodness. And in that case, this is 2 pi I. So I literally have an infinite sum, both in the positive sense and in the negative sense, 2 infinite sums of zeros plus 2 pi I times its coefficient. And so I end up with c to the minus 1 times 2 pi I, or as your book writes, 2 pi I times the residue at z equals z naught of f of z. Now that's remarkable. So here we go. If you want to integrate a function on a closed curve living inside your deleted neighborhood of z naught, then the integral is just 2 pi I times the residue of z minus z naught of f of z. So I'll stop the video here. We're going to say this a little more succinctly in the next video. This is known as Cauchy's residue theorem.